What I discussed yesterday, so basically we established that there is a glass transition in a two-dimensional electron system in silicon at zero temperature for all densities below some density Ng, which is on the metallic side of the metal-insulator transition. In other words, we show that here in this system, an intermediate glassy phase emerges, which is also metallic with some kind of a strange temperature dependence. So the glassiness was established by finding non-exponential relaxations, scaling, diverging equilibration time in the zero temperature limits, and we also looked at aging and found that the aging properties change at the metal-insulator transition. Here is just a description of what I had yesterday of this waiting time protocol, which is the protocol that Michel called intermediate, where we change the density to some value during the waiting time, and then we go back to the original initial value and look at the relaxations. So those aging studies were done at temperature 1 Kelvin because I showed you that the equilibration time is astronomical at that temperature, so the system is always out of equilibrium. Of course, you can ask also a question, what happens at lower temperatures as we approach this ideal glass transition? Well, here is an example of the data obtained at lower temperature, and here on the left side I have the time dependence of the conductivity for several different densities. These are initial densities, so during this waiting time here in the middle we go to the same high density, relatively high, and then we come back to the original density. So you see these data on the left before this perturbation were obtained simply after cooling the sample to the measurement temperature. So you can see that there are no visible relaxations after this cooling down, but you can also notice that since these are divided by their corresponding average values, at high densities, the curves look kind of flat, but at lower densities, they become much noisier. And then when we change the density during the waiting time and we come back to the same densities here, at these high densities we see some relaxation, which we actually subtracted from the top 3 traces because we wanted to focus here on the noise. And you can see that after this perturbation, the noise is much bigger than before. In fact, so much bigger that for these two lowest densities we divided the signal by a factor of 10. So after the perturbation, during this aging process, signal is much noisier than it was before the perturbation. You can also see that here there are no visible relaxations, so it is impossible actually at low temperatures to study the relaxations because the signal is so noisy. So you're kind of stuck with these fluctuations, and if you want to learn something, you have to study the fluctuations. You cannot study the relaxations. So this is what we did at lowest temperatures, and of course this is going to provide us with some complementary information because the measurement of the resistivity is just really the average, the mean value. Okay. So, and here is one example. Michel mentioned leptonite earlier today. These people studied the noise during aging, and these are the distribution functions, the PDS, as for 3 different ages of the sample. So you can see that as the system ages, this PDF, which was very non-Gaussian, approaches this Gaussian value. So it goes from non-Gaussian to Gaussian. So some people like to study this and see which class, university class this falls into and try to learn something about that. So anyway, so we at low temperatures measured noise, and here is a detailed description of the noise protocol. So basically, you cool the system down from high temperature and measure the conductivity as a function of time. That's it. And then you want to change the density, so you have to warm up. Now, in previous protocol, we warmed up to 10 Kelvin. In this protocol, we changed the density in tiny steps at 1 Kelvin. And we found that there was really no difference in the results as a function of density. So So this is how the experiment was done, and this is actually the first thing that we ever did. You can see this was done a long time ago, before we did these relaxations. The temperature, so these are the relative fluctuations of conductivity, relative with respect to whatever average value you can get out of traces like this as a function of time. This was done for low mobility samples, that is samples that had a lot of disorder. These traces are taken at very low temperature, 0.13 Kelvin, and they correspond to different densities. And they're also shifted vertically for clarity, so we can look at the noise. So you can see that at the high densities, the noise is not that big, but when you go to low densities, it's huge. This is of the order of 100%. So when the noise is so big, there is nothing else you can do but study it, make a friend out of it. So the noise is very big. It's also non-Gaussian. You can see that it also takes place on all kinds of time scales. It changes, the variance changes with time. For example, if you do your measurement here, it will seem that the noise was not that big. But if your measurement is done over this time interval, it will seem really large. So at the beginning, we didn't really have very ambitious plans. So the first thing we looked at was just the variance to see how it depends on the density, because obviously it was bigger at lower densities, and we also noticed that it was getting bigger as we reduce the temperature.
Excuse me, is there any future in looking at power spectra of these?
Yes, in a few slides.
Oh, okay.
Well, see, this was a long time ago, so we evolved. Okay. So this was just the beginning part. I'm showing it because it still, shows dramatic behavior. So this is the noise, standard deviation divided by the average value over a fixed time interval. And you can see that at high densities, within the error of the measurements, there is no density dependence. And then at some density, the noise starts to increase exponentially. And this increase is bigger, see, it's steeper for lower temperatures. So for those of you who remember what I said yesterday, this density is that separatrix, where temperature dependence on conductivity changes sign. This is Ng, where we found that, above Ng, there are no relaxations. Below Ng, we saw these slow non-exponential relaxations, aging, and so on. And then C, about 5, corresponds to the critical density for the metal-insulator transition. So we saw this huge increase, but also, so we were surprised that these two densities, were not the same or nothing was happening here. If you look at the variance or standard deviation itself as a function of density, for different temperatures, we did not see any temperature dependence, at least in this range, but you can see that this slope changes dramatically exactly at NC, the critical density for the metal-insulator transition. So it also kind of makes sense, it's kind of plausible because the electrons are becoming strongly localized, so it's more difficult for them to move around. But that's all I can tell you about that. So, okay, so for all those of you who like to look at PDS, this is what we get. So for densities above Ng, we get nice Gaussians, and I'm not sure why I did not include that here, probably because I thought it was, not interesting. But for all densities below Ng, we get some complicated structures that depend on when you do your measurements. So for example, over the first interval, each one was about 35 minutes, you get something like this, then you do your measurement later, you get something like that. So the structure changes with time, and you can see how it changes is here. So these are 35-minute intervals. So as a function of time, it wanders around. And you can say, okay, but maybe after all this time, which is about, 8-9 hours, maybe you get a nice distribution, but you really do not. So this is as a function of time. So this is 0, and here we are just, increasing the time. You can see even after about 8 hours, there are still, like 2 big peaks and a lot of structure in between. So on experimental time scales, it never becomes Gaussian. So if you want to study PDFs, tough luck, because they don't really have a nice shape. They change all the time. So I think that's, not useful in this case.
Looks like we have 2 characteristic time scales.
1, 2, 3, 4, 1, 2, I don't know.
Well, at any one time, there seems to these guys seem to be time model
Yeah, because there are probably very few small number of states that contribute at a given time, as we'll see later from the noise. So that's, that makes sense. I mean, it's consistent with other things here. So yes, okay, so when you have a time series, just like yesterday when you have similar curves, what do? You try to scale them. Now when you have time series, you look at calculate the power spectrum. So this is the power spectrum at the lowest one of the lowest temperatures for different densities. So it's a 1 over F type. And you can, people usually look at as a measure of the magnitude of the noise, the fixed frequency, and see how the power changes. So for a fixed low frequency, as a function of density, just as what I showed you before for the variance, there is no dependence in high densities. And then below Ng, which is here, we see a huge exponential increase of the noise at low densities. So in the classy regime, the noise goes up rapidly. And the inset shows that for a fixed density, say one of these, as we lower the temperature, it also goes up exponentially. And this happens also to rule out some simple mechanisms for the noise. Okay, so what we see from here is that the noise slows down dramatically below this density. The dynamics slows down dramatically below this density Ng. And the most spectacular, I think, is the behavior of this exponent alpha as a function of density, which is shown here. So you see for high densities, this exponent is 1, so it's a pure 1 over F noise, if you like. And then at Ng, the noise jumps up to a very high value, about 1.8, which suggests that we have a very small number of states that give rise to that contribute to the transport. So this behavior is very sharp, and actually this is, this was, the first, I think this is much better evidence for the glass transition. It's sharper than those relaxation curves. I mean, this is much more dramatic. The inset shows the temperature dependence of this alpha. For example, for a density, if you fix the density here and you raise the temperature, it gradually decreases. So this transition is no longer very sharp. But this behavior as a function of temperature is very gradual. So to us, this seems to indicate that the glass transition really takes place at zero temperature, because there is nothing dramatic happening at any temperature, and this was later confirmed with the measurements of the relaxations and equilibration times.
I can't remember, what does the mean conductivity do around Ng? Is there also something sharp that happens there?
The mean conductivity, okay, I don't have it in this one.
Yeah, I can't
there is
remember.
nothing sharp, but if you look at the temperature dependence, you can see that it's changing, because below Ng you get this T to 3/2. So you can see that it's different. The curves kind of start to peel off one from another. So, but these are more subtle effects. I wouldn't dare to claim based on something like this, yeah, there is something special going on there. Or at least not as sharp as this. Okay, so the dynamics, obviously suddenly dramatically slows down at Ng. So this shows us now that we know, what we know from yesterday, that we can use noise also to identify the glass transition, because this happens precisely at Ng. So this is what we did actually in the measurements of high mobility samples with low disorder, because in those samples we have not done relaxation measurements. Okay, at least we have some data, but we haven't published them yet. They are getting old. So anyway, for high mobility samples, we use the noise to identify the glass transition, and here some traces, it's similar to the other situation. High densities are here on the bottom. You can see that as you reduce the density, noise becomes bigger, becomes non-Gaussian. Then you look at the power spectra again. Here we multiply by F, so 1 over F is flat. Here, so you can see immediately that the exponents are between 1 and 2. Then you repeat everything. So basically, you repeat everything here. So here we are looking at the magnitude of the noise at some low frequency as a function of density. Again, you see that there is some density where noise goes up exponentially, goes up rapidly. Many others, the magnitude over a small range of Densities, the same thing happens with the exponent alpha of the noise. It goes from 1 to a much higher value. And also the temperature dependence is the same as in low mobility samples. It increases again exponentially at the lowest densities as temperature goes down. So we can, if we use these noise results, we can identify again glass transition, and we find that in these samples the glass transition is very close or just slightly above the critical density for the metal-insulator transition. This is what I was saying yesterday, that in these samples with low desolder, this intermediate phase, metallic glassy phase, essentially disappears. That the metal-insulator transition and the glass transition more or less coincide. So, okay. Now we want to look at the non-Gaussianity in a little more detail, and here are again a few traces obtained on high mobility samples. Here we are dividing by the standard deviation because so that these are more or less the same on this scale. The reason for that is we want to focus on the shape of the noise. I mean, you can see now clearly that at the high densities the noise is Gaussian. And then as you reduce the density, it becomes non-Gaussian. You start seeing slower modulations on top of the rapid ones. So the variance changes with time, and this tells us that by looking at higher order correlations, we can learn something about this system. And we followed actually closely the work that was done by Michael Weissman on spin glasses. He wrote 2 review papers. The first one is on 1/f noise in solid state. And the second one is basically using noise measurements to probe the dynamics of spin glasses. So we, did what he did, and I copied this from one of those papers. So we looked at the second spectrum, which is a 4th order noise statistic. Sometimes they call it noise of the noise, because it's really a power spectrum of the fluctuations of the first spectrum with time. So you all should have no problem understanding what this is, but for me it's easy to understand it. You say, okay, today I do the measurements over this time interval, we calculate the power spectrum, and we find its value at some given frequency f. We come back tomorrow, you repeat the measurements, it gets some value here, and so on. So here you have another time series, and you take the power spectrum of that. So if the fluctuators are uncorrelated, if you always get a contribution from the same states, then this will be essentially the same. Maybe you have a Gaussian distribution because you have a finite number of data points, but the spectrum of that should be white. On the other hand, if different states contribute as a function of time, then the second spectrum will be also 1/f type with some exponent that people call 1 minus beta. So the main point to remember is that if you calculate this, then this 1 minus beta can be a measure of the correlations. Okay, so if there are no correlations, 1 minus beta is 0, and if you have some, then it's bigger than 0. So we've done that, and this is just an example, a couple of second spectra for 2 different densities. The main result is here. So this is the value of this 1 minus beta, the measure of correlations, for 2 kinds of samples. In samples with high mobility or low disorder, you see that this is 0. So the noise, which we already saw just by looking at the data, we saw that it was Gaussian. You can see that the correlations, there are no correlations. And then at the density, which more or less is the same as NC, we see that the noise becomes correlated. And similarly, in low mobility samples where we have this intermediate metallic glassy phase, at high densities, there are no correlations. This is Ng, and below Ng, we start seeing the onset increase of the correlations. So everything fits nicely. At the same density where the dynamics become slow, it also becomes correlated. This second spectrum was used by Michael Weissman in spin glasses to try to...
Oh, sorry. I was just wondering if the power spectrum had any waiting time dependence. So you're measuring it at different times.
There is no
I don't know.
waiting time here. I mean, we don't really measure it in different times. We just measure for a long time, and then you split this up. And but there is the waiting time is the same. If you say, okay, it's the time gauge, after you cool it down, it's the same. Or maybe you can define it differently. But again, after the cooling down, we did not see any dependence on the cooling time. We varied the cooling times between about 30 minutes to 8 hours. We did not see any dependence on that. So this is why we needed a different time where it actually had some effect that we could control. Again, I think maybe this is because this perturbation is just so small to see change in the temperature compared to the relevant temperatures here. So anyway, so in spin glasses, Mike Weissman used the second spectra to try to differentiate between two different known models, pictures of glassy dynamics, namely hierarchical pictures and the so-called droplet pictures. So in the hierarchical picture, all these states are in a tree-like structure, so everything looks the same on every time scale. The structure of the tree is the same, so there should be no dependence of the correlations. There is no characteristic frequency, no characteristic scale. On the other hand, now all this was his hand-waving argument, which makes sense, but as far as I know, nobody has actually calculated this, which is a little annoying after all this time. Okay, it's been, I don't know what, more than 10, 15, 20 years, I don't know. So anyway, now there is the other model is the picture of droplets, interacting droplets, and they assume that there are short-range interactions there. So you have droplets of different sizes. So the low-frequency noise will presumably come from the bigger droplets because they're slow, but they will be also more likely to interact, as opposed to the smaller droplets, which are faster because they're small, but they're less likely to interact. In other words, the correlations at lower frequencies would be bigger because you're looking at bigger droplets. So this second spectrum would decrease as you increase the frequency. So
also, for the high mobility samples, if you apply a magnetic field,
that will come later. Okay. I mean, I'll show you, then ask, if I don't answer your questions, ask me again. Okay, so basically we did this. We calculated the second spectra for different frequencies of the first spectrum, and the data are scattered, yes, because it's noise of the noise, but there is no systematic dependence on the frequency. So we conclude that just like the situation in spin glasses, we find that this glassiness is consistent with the hierarchical picture of glassy dynamics. So this seems to rule out the various models of interacting two-state systems, droplets, clusters, things like that. And you will see later that the situation in cuprates is different, if I have time for that. Okay, we come to the magnetic field now. So I told you we have a simple system. We have electrons. They interact with Coulomb interaction. They feel the random potential, but electrons also have a spin. So in order to kind of narrow down whether this glassiness is due to the spin or charge degrees of freedom, we perform measurements in a parallel magnetic field, because that way we get rid of orbital effects and the field couples only to the spin. And it is known that in conventional spin glasses, sufficiently strong magnetic field can destroy the spin glass solder, and it does. And we also have the advantage here that a lot of other people have studied these same samples, and they determined that at relatively low fields in this range of densities, all the electrons can get fully spin polarized. So they all point in the same direction, so it's like having a system of spinless electrons. So for each density, then you repeat the measurement of the noise for many different magnetic fields, and then for many different densities. So this is one example. Zero field, and you apply some fields, you can see that the noise changes, the power spectrum changes, alpha changes. So you repeat all these for lots of densities, and you repeat the same analysis. And we want to use the noise, again, as a criterion for the glass transition. In other words, we want to look at the magnitude of the noise And for example, so this is for as a functional field for different densities. So for example, for one density, when the magnitude jumps up to a high value and the exponent alpha also jumps up to a high value, the correlations also jump up, become non-zero, then we say, okay, for that density, this is the magnetic field where the glass transition takes place. So in this way, you can map out the phase diagram, which is what I showed you yesterday. So these green points, green squares are the data that we obtained from this kind of analysis. So this is where the glass transition takes place. This is the metal-insulator transition. And you can see that exactly at about field about 3 Tesla, when the system is fully spin polarized, nothing depends on the magnetic field anymore. The values of these densities. However, the glass transition persists. So even when the whole system is spin polarized, we have essentially a system of spinless electrons, the glass transition persists, and this tells us that it is the charge degrees of freedom as opposed to spin that are responsible for this glassy ordering, so we do have a Coulomb glass. Okay, let's see, I'm doing behind. So this is a theoretical phase diagram, which has some relevance, I think, to what we have been doing, and this is the work that has been going on for a number of years in a group of other Bresavich, also at FSU. So this is the phase diagram for the metal-insulator transition, the MOS transition, so all interactions are important with the solder. And theorists always have a different way of plotting things, which is not which is different from what we do in the experiment. Basically, for sufficiently large desolder, they find that they find the emergence of this intermediate phase, which is metallic and glassy. In the experiment, we changed the carrier density. So the experimental trajectory will be like this. Okay, so if we have when we have a lot of disorder, we will be going this way by changing our density. So we go from high density, reduce it, and we go through this metallic glassy phase into the insulator. For low disorder, we will be here on the phase diagram, and this metallic glassy phase will be very small or even non-existent. So the existence of this intermediate phase, its dependence on the disorder are consistent with what we found in the experiment. Also, for this intermediate phase, as I mentioned yesterday, they find this same temperature dependence that we found, and also the type of model that they used to obtain this kind of phase diagram is known to produce hierarchical dynamics for glasses. So the main features are consistent with what we have found. And this phase diagram is independent of the dimensionality, so this is expected in both 2D and 3D dimension. 3D. Now,
can I ask, U is
U is the Coulomb interaction. Is the Coulomb interaction. This is the disorder, and that's all I know about that. And
I guess the Anderson transition is way over to the.
Well, yeah. Okay, maybe here, because here the Coulomb interactions are important. So in Anderson transition, they're not. Just disorder driven. So this is for a twin system. You have basically a Wigner crystal, melting of the Wigner crystal. So that's all I know. And I also know that this is a dynamical mean field theory, which is supposed to be the theory for strongly correlated systems. Okay. So there have also been some simulations. Again, this was done by Cynthia and Charles Reichardt. These are molecular dynamic simulations that were actually motivated by noise work. And they looked at the classical model of interacting electrons in 2D with disorder. So it's a classical model, but nevertheless they were able to reproduce some of the main features of the data. They found that as you approach the as you reduce the density, the magnitude of the noise goes up, the exponent alpha goes up, and the metal-insulator transition, and and also as a function of temperature. And they were also able to find non-Gaussianity at low values of densities and temperatures. So this is very similar to experimental data. The details are not quite the same, like alpha is 0 here. But anyway, so it's similar to the experiments, and as those of you who work on such things know, they can obtain, if you look at electron trajectories for a fixed period of time, so this corresponds to the case when you have a high density of electrons. You can see that electrons can more or less move freely throughout the sample, except that some may get stuck for a while somewhere, but essentially they can flow easily. As you reduce the density, this splits into a kind of mixture of 2D, 1D paths. And at even lower densities, the motion is mostly through 1D channels. Other electrons get stuck somewhere in the sample, and then at the lowest densities, electrons are localized. So you can see, it's easy to see from here why the noise is big. I mean, here you basically have like two channels that percolate through the sample that dominate, that determine the conductivity. So if one of them shuts off, there will be a huge change in conductivity. This is why the noise is big. And of course, so this is done for a fixed period of time. If you look at some later time, the picture looks different. So they find evidence for these dynamical inhomogeneities, which is what people have found in many other kinds of glassy systems. Now, in addition to this,
it's probably a little bit of a digression, but how on earth do you measure something like that?
they?
How? Yeah. Or how does one?
Well, we measured noise. We measured fluctuations of conductivity, and this is the, this shows the electron trajectories. They get this. I don't know how they get these pictures from molecular dynamic simulations. I think there are some equations that tell you how they move. Right. So anyway, there is also another kind of simulation, Monte Carlo, which I understand is different from this. And they also find, for a 3D Coulomb glass, they find a similar kind of heterogeneous dynamics. They find that some electrons move more or less freely through some kind of chain-like path. Others get stuck. As a function of time, some paths shut off, the others open up. So this is all consistent with that. So this is all that I'm aware of. Now, what about experiments in other systems? Somebody asked about Columb. This group, also at Clay, tried to measure noise in a 2D Hall system of gallium arsenide. They did find some increase of noise as the Hall concentration was reduced and the temperature was reduced, but they did not find any evidence for glassiness similar to what we have found. Now, we could say maybe they didn't go to low enough densities, temperatures, frequencies, whatever. But I think it's more likely that the samples were too clean. There was simply not enough disorder. So one way to find out would be to look at this kind of system with more disorder. But guess what? As Michelle was saying, they've also stopped working on this. They're working on something else. So guess who will have to do this? One day. So now this is the most exciting to me because we are back to that dope silicon that I started my first lecture with dope silicon that has been studied like forever. And after our noise work, these people decided to look at noise in phosphorus and boron dope silicon. And what they found is that, yes, as you approach the critical density, as you get to the critical density for the metal-insulator transition, the magnitude of the noise goes up, many orders of magnitude. Also, the exponent alpha increases. The exponent 1 minus beta goes up, which means noise becomes correlated. So it's very, very similar to what we found in our 2D system. So it seems that this may be a general feature of metal-insulator transitions if you have enough disorder. But I don't know if they'll be continue working. I know that he's doing some noise work, but not on this. So I come finally to this. I also talked in the first lecture about, I gave examples of some other strongly correlated systems that exhibit complex behavior. And there is no single question here. There are many questions. Not just the question, what is the pairing mechanism here, but also this normal state exhibits all kinds of strange properties. I mentioned also in the first lecture that people have seen the emergence of all kinds of nanoscale inhomogeneities. When I say all kinds, I mean in many different quantities that they measured. So it has been established, for example, very well that at low temperatures the spins freeze. And you have the coexistence, and the spin glass phase extends all the way to this optimal doping. So here you have the coexistence of superconductivity and spin glass behavior. Now there are also some experiments that show the presence of some charge inhomogeneities. I showed some STM images before. These are local probes. There are also other probes, so like nuclear quadrupole resonance, which is a local probe, and they also find evidence for charge inhomogeneities, but this is all done at very high temperatures. So in this paper, they looked at the available experimental data, and it seems that perhaps these charge inhomogeneities vanish only also here at optimal doping. Now, if this scenario is true, this would mean that the insulating phase here, which may be a charged glass also, is separated from this nice metallic phase at very high doping by some inhomogeneous conducting glassy state. So you would have two transitions, right, from an insulator to a conducting state, and also transition from a glassy phase to nice metal. So why is this interesting? Well, there is this analogy between what I was describing for a 2D system, where you have metal-insulator transition, glass transition separated by this conducting phase, which is inhomogeneous and glassy. So for me, this similarity was intriguing because these materials are so complex, it is very difficult to understand, so I think it would be useful to try to see which of the properties of these materials are common to other strongly correlated disorder systems, and which ones are specific to those that exhibit the phenomenon of high temperature superconductivity. So in other words, we want to see if there is some kind of universal behavior. So what we wanted to do is basically look at the ground state and then see whether at low doping we have a glassy insulator, and then if we do, to see how this evolves as a function of doping. So the material that we selected is this lanthanum cuprate, which which has these planes of copper and oxygen atoms where all the action takes place, and usually it's doped with strontium, which substitutes these lanthanum atoms. And this was a good choice for our studies because this material has been studied for more than 20 years with all kinds of techniques, 1 million people. So it's very well. I thought it was very well characterized, but not as well as I expected. But anyway, it's been studied very well. And also, these just like in doped silicon, these dopant atoms are distributed randomly in the material, so you have some intrinsic disorder. And we wanted to have disorder because our goal was to find the evidence for charged glassiness. So we wanted to optimize the conditions for the observations of that.
When you say here the dopants are also substitutional? Or?
Yeah, they substitute for lanthanum. Yeah, so it's so this one, it has 1 series valence is 2, this is 3, so it gives one hole then donates one hole to this copper oxygen layer. Now the undoped material is an antiferromagnetic insulator. Now it turns out that in each copper atom you have a spin, and they are antiferromagnetically ordered in the plane. Now, because of the details of the lattice structure, the total moment is slightly out of this plane. So there is a small component which is perpendicular to these copper oxygen planes, small ferromagnetic components. And these ferromagnetic components in neighboring planes are opposite, so they're also antiferromagnetically ordered, so the total magnetic moment is 0 in the material. Okay, so this is the undoped material. Then you put a little bit of doping, like 2%, you kill this long-range order. But even after you kill it, like in this regime, people have determined that short-range antiferromagnetic order persists. So you have domains. Each one has, a component of the spin pointing along the z-axis. And there are many experiments that suggest that these doped holes actually live along these domain walls. So this is just interferomagnetic ordering, short range, just like in this undoped material. We put holes and they, they live in these domain laws.
Question, just to make sure I understand something. Like in your previous discussion of the silicon, you found this Coulomb glass. But in principle, here in the cuprates at zero temperature, you never have the Coulomb glass spin glass.
We know that we have spin glass. The question is, do we also have a Coulomb glass? Now, in other words, this is related to the question I mentioned. We know that these spins are elastic. So if we measure transport, if we measure the response of the charge, if we see glassiness, if that's due to the fact that these holes are just following the slow motion of spins, or is there something else? Is it because, would they become glassy because of the Coulomb interaction, just like they do without these spins? So, it's a challenge, first of all, to establish glassiness and to try to separate these two. And I think we have done that. And I'll show you, I hope, quickly. Okay. So what we want to do, we want to work here. 3% doping where we know we are in the spin glass regime. So we work at temperatures, below the spin glass transition temperature. And the system is insulating. So what we do, we measure, I'll keep a few things, but we measure transport. You can measure transport in the plane. And you can try measure transport along the c-axis or perpendicular to the planes. So here is an example, more tedious measurement. So this is a so-called outer plane, and this is in plane. So these are the fluctuations of resistance as a function of time. Again, we have some long time scales. Different curves correspond to different temperatures. They're again shifted for clarity. And this lower graph is just the blow-up of this region here, so you can see there is all kinds of, a lot of structure there. So you can see that in both cases at high temperatures, which is here, the noise is Gaussian. Then we lower the temperature and it becomes non-Gaussian. So this is very similar to, what happens in MOSFETs. However, here, this happens at lower temperatures. So again, this non-Gaussianity tells us that we have a small number of metastable states that contribute to the conduction. So the system, at least on experimental time scales, is out of equilibrium. So we do, repeat the same thing again, get the same results. The structure of PDF depends on the time. We can have 1, 2, 3 peaks. So on the experimental time scales, you cannot reach, equilibrium. And these are the PDFs at the lowest temperature for the time, measurement time up to 12 hours. You can see on experimental time scale it's not Gaussian. Only when you raise the temperature, and you cannot see it here, it becomes Gaussian. So again, here these PDFs are useless. Okay, so what we find is that this non-Gaussianity in the noise becomes observable at temperatures that are much smaller than the spin glass transition temperature, which is about 7 or 8 Kelvin. And this suggests that the spin and charge glassiness are not directly related. So we continue, with the same kind of analysis that I just presented for silicon MOSFETs. We looked at the power spectrum. We want to see how this exponent alpha, it's 1 over f. We want to see how alpha depends on temperature and magnetic field. Again, these are results for transport noise out of the plane perpendicular to copper-oxygen planes, and this is in copper-oxygen planes. Red points show how alpha depends on temperature. You can see that in both cases, alpha increases gradually to, again, a large value. It's very similar to what we saw in silicon MOSFETs. On the other hand, the effect of the magnetic field at low temperatures on this alpha within the error, does not exist. So this means that since alpha grows, fewer and fewer metastable states dominate transport at low temperatures, at least in the experimental time window. So this, just as we saw before, tells us that the dynamics is slowing down gradually as temperature goes to 0. Now you can look at the second spectrum. You can look at, I don't have to show all this again. Okay. So again, 1 over 1 minus beta is the measure of the correlations. This is again transport in the plane, out of the plane. Red points show the temperature dependence. The correlations grow as we reduce the temperature. And again, the magnetic field does not have any effect on 1 minus beta. So we see increase of correlations, and also the magnitude of the noise does not here seem to depend either on temperature or the field. So we established that the noise statistics is independent of the magnetic field, and we also established that it's independent of the magnetic history. For example, these data were taken after zero field cooling. We have also done field cool measurements, and in fact in magnetotransport we see a strong difference in the resistance between field cooled and zero field cooled data. However, this history has no effect on the noise statistics. So what we conclude from the noise data is that we see slowing down gradually of the dynamics as temperature goes to zero, increase of correlations. So this suggests that there is a glass transition at zero temperature. And the fact that the noise statistics is independent of both B and magnetic history, which is very different from what happens in conventional spin glasses, suggests strongly, I think, that this glassiness is due to the charge and not spin degrees of freedom. And this is further supported by the fact that also the hysteretic and memory effects that we observed in magnetoresistance and that I have not shown to you also start being observable at temperatures that are much lower than the spin glass transition temperature. So all this happens deep within the spin glass phase as you go towards the zero temperature. So this suggests that here also there is a charged glass transition that occurs as a result of Coulomb interactions, and it seems to be taking place again at zero temperature. So what about scaling? Okay, can we say something about that? So I already mentioned that before. And here are the data, and I hope you can see that even though they're noisy, they're very different from what I showed you for silicon MOSFETs, where even within the noise, there was no systematic dependence on frequency. And here we see a clear dependence for both in-plane and out-of-plane transport. So it seems that in this case, the data are consistent with the droplet picture, which assumes the existence of some short-range interactions. And in fact, this is not so strange because people do believe that there is an effective short-range attraction between holes in these materials, and we also know that we do have a Coulomb interaction. So the conclusion is that these holes turn into clusters, they cluster, as a result of the competition between interactions on different length scales. And in fact, there is a theoretical paper, Schmalian and Loines, where they show that even in the absence of disorder, when we have a competition between interactions on different length scales, this can give rise to glassy dynamics. So what we conclude is that this charged glass is somewhat different. This is a cluster charged glass. And I also want to mention that the spin glass in these materials is not the same as spin glass in conventional spin glasses. It is also a cluster spin glass. So things are different, and I'm running out of time, but basically, what I showed you today is that noise can give us very useful information. We can use it to identify the glass transition. So we found glass transition as a function of density. It also helps us differentiate between different theoretical models. In the case of a pure Coulomb glass, with no magnetic degrees of freedom, we found that this fits the hierarchical models of glassy dynamics. On the other hand, in this lightly doped cuprates, we also found evidence for the formation of a Coulomb glass, but this is a cluster charged glass because of the presence of other interactions in the system. And I also mentioned using noise to probe glassy dynamics in other systems. This was most exciting to me. So our plan, 5-year plan, our plan is to, now that we establish this charged glassiness in the lightly doped regime, we want to move on to higher dopings and see how this state evolves as we approach the superconducting transition. And also, we want to keep on working on this system because I hope maybe you appreciate a little bit more now that this is a simple system compared to this. Yes, because it's simpler. So that's our plan, and I encourage you to keep on working. Again, I don't know why I'm saying this because I kept saying this is tedious and so on, but it's really exciting once you can, get some information out of it, and I think we have been able to learn something. So it's very satisfying once you reach that point. But it takes a lot of hard work. So, but I think it's worth it. So thank you very much for your attention.
So, are there more questions or comments? We have time. Yes?
I have a question about resisting fluctuations. Your noise seems to be like step functioning or something like that. Just sticking in some.
No, where? For which system?
Glasgow.
Excuse me? Oh, this is just okay. Yeah, don't take it. Well, I don't want to say don't take it too seriously, but sometimes you see this. Sometimes you see these switching effects, but you don't see them always. In fact, most of the time you don't. So, and this could be, because we have these magnetic domains and these spins maybe, flipping also.
Spins or domains, actually?
Well, the spins, but then they should affect the domain too, because these are, yes, so, because it should affect the domain walls also. These are anti-phase boundaries, so everything should change. So I think, I'm not sure, maybe it's because of that, I can only guess. But yes, here we did see some switching, but most of the time you don't see it. And also this is the autoplane transport, and these materials are difficult to understand, but they're even more difficult to understand in the autoplane transport. Most theories like to kind of stay in these planes. So we've never seen that here. So this is maybe not the most important thing.
Anyone else? Yeah.
High temperature superconductivity has been challenging theorists for many years as well. Has this Coulomb glass phase generated any interest on the theoretical side?
This is very new, and I think so. Actually, we got really very positive response from the referees. Well, because it's very different. It is very different for them. Okay, it's a different community. So they've never seen noise, or they don't know much about. So it's original, novel. So, and it's also consistent with other work. For example, with these STM pictures, people do it over a fixed period of time. But I'm pretty sure they will try to do it also at lower temperatures. Maybe they will see some dynamics. The NMR people like this because they've been seeing these dynamic inhomogeneities for a long time, but at much higher temperatures. But people always criticize one another. Like these are local probes, so they say, oh, it's a local probe. That's STM, oh, that's a surface probe. It's no good. Okay. So it's good to have some complementary probes. Like this is a bulk probe. It's something on different time scales. So it's good. Yeah.
Yeah.
So for the 2D electron gas of silicon, the glass state is due to the cooling direction due to the charge, not spin. But it seems the glass transition is still, it seems the magnetic field is still has some effect on the glass transition units.
Not after you fully spin polarize the 2D system. Then it's flat.
For parallel magnetic field, parallel.
Right. Yeah.
It still has some effect on the transition. So is it because the magnetic field will affect the density of states or density of carriers or affect, or still have some small optical effect? So what do you think?
It also affects the metal-insulator transition, and I know this also happens in dope silicon, that the system becomes more localized, the critical density goes up. But here, it's the parallel field, so maybe it would not localize it. So, maybe spin plays some kind of a role in that case. It reduces it has been shown that it reduces the screening. So you can say the effective disorder is bigger, so this is why the critical density is going up, and this is why this intermediate phase grows. So this is a plausible explanation, and there is even one theoretical paper published on that. So I think that's the most plausible explanation, that affects the screening because it polarizes the electrons. But after you polarize them, nothing changes anymore. So.
Others? Yes?
In one of the phase diagrams that you showed for the cuprates, it seemed that the spin class went all the way down up to zero doping.
They find some kind of a freezing also there. I mean, it's not spin glass because we haven't shown this scaling, but the spins freeze. So all the way to. I mean, that's correct. I mean, this is what other experiments show. So.
In the other diagram, it was like the antiferromagnet at zero doping, right?
Yeah, I mean, this is the accurate, actually. Okay, let's see. No, what's wrong with this? Okay, this moves. I put spin here, but this letter, this one should be kind of here. Because they say, okay, this is the freezing, but this is really a spin glass. But okay, who cares, for our purpose, they are frozen. So.
Any more? No? Let's thank Dragana again.